Welcome back. In this video, we'll explore the fascinating world of pulley systems, how they function, and the various ways they're applied in real-life scenarios. So, without further ado, let's get started. Now, imagine we have a heavy object that needs to be lifted. Lifting it directly demands significant effort to counteract the gravitational force pulling it downward. What if we could use a simple mechanism to make the process easier, even leveraging our own weight to assist? That's exactly where a pulley comes in. A pulley changes the direction of the force required to lift the object, making the task significantly easier to handle. Before we dive into pulley systems, let's clear up a few assumptions we'll be working with. Now, I know these might sound a bit unrealistic, but they're really useful for simplifying things and helping us understand the basics. First, we're going to assume that the pulley has no weight. Of course, in real life, pulleys do have weight, but compared to the load they're lifting, it's usually pretty small. So for now, we'll treat the pulley as weightless to make our calculations easier and avoid worrying about rotational inertia or extra load. Next, the rope or chain running through the pulley. Let's assume that's weightless too. And not just weightless, but inextensible as well. What does that mean? It means the rope won't stretch, and its mass won't mess with the tension. This way, we can keep things simple and assume the tension is the same throughout. We're also going to say the pulley and its axle are frictionless. In real life, there's always some friction, but ignoring it for now lets us focus on the mechanics without worrying about energy losses or reduced efficiency. So, why are we making all these assumptions? A weightless pulley. That's to avoid dealing with its rotational inertia. A weightless, inextensible rope, that keeps the tension consistent and avoids unnecessary complications. A frictionless pulley, that helps us focus on the forces and motions without the distractions of energy losses. By sticking to these idealized conditions, we can really focus on the basics: forces, tensions, and movements. Once we've got that nailed down, we can start bringing in the real-world stuff like friction, pulley weight, and rope stretch to see how they change the picture. There are three primary types of pulleys, each with distinct features and applications. The fixed pulley is the simplest type, where the pulley is stationary and the rope moves over it to lift a load. Its primary function is to change the direction of the applied force, making it easier to lift an object. For example, instead of lifting upward, you can pull downward, which is often more convenient. However, a fixed pulley does not provide any mechanical advantage, meaning the effort required to lift the load is equal to the weight of the load itself. The movable pulley, on the other hand, is attached to the load itself and moves along with it. This type of pulley provides a mechanical advantage by reducing the amount of effort needed to lift the load. The force required is effectively halved because the load is shared between two segments of the rope. Movable pulleys are often used in systems where heavy lifting is required, such as in construction or sailing. Lastly, the compound pulley is a combination of fixed and movable pulleys arranged into a single system. This configuration significantly increases the mechanical advantage, allowing for much heavier loads to be lifted with minimal effort. Compound pulleys are commonly seen in cranes, elevators, and other heavy-duty applications where efficiency and reduced effort are essential. The main point to note is that fixed pulleys are mainly used to alter the direction of the applied force, which makes lifting or moving a load more convenient. However, they do not provide any mechanical advantage. In comparison, movable pulleys are highly effective in reducing the effort required to lift a load by offering a mechanical advantage, making them indispensable for tasks where minimizing effort is essential. Having explored the different types of pulley systems and their applications, let's now dive into the mechanics behind these systems. Understanding the mechanics will help us analyze how forces and tensions are distributed in pulley systems, how mechanical advantage is achieved, and how these setups simplify heavy lifting tasks. By breaking down the principles step by step, we can better appreciate the efficiency and practicality of pulleys in various real-world scenarios. So let's get started. we'll use this compound pulley system as a model to explore and understand the physics behind pulley systems. By analyzing how forces, tension, and mechanical advantage work together in this setup, we can gain a clear insight into how pulleys make lifting tasks more efficient. In this system, we will denote the attached weight as W, representing the load that needs to be lifted, and the applied force as F, which is the effort exerted to lift or balance the load. This force acts along the direction of the rope, and in an ideal pulley system, the tension remains uniform throughout its entire length. This principle relies on the assumptions we discussed earlier. Friction in the pulley is neglected, and the rope is both weightless and inextensible. Even when the applied force is at an angle, the tension in the rope remains constant along its entire length. According to Newton's third law of motion, when you pull on a rope with a force F, the rope pulls back with an equal and opposite force. In this case, this opposing force is the tension in the rope. The tension acts as the balancing force that keeps the rope in equilibrium at that point. Therefore, the tension in the rope equals the applied force F, ensuring that the system remains stable. In this example, the weight is attached to a movable pulley, which is supported by two sides of the rope passing through the pulley. These two segments of the rope effectively share the load, distributing it equally between them. The relationship between the tension in the rope and the weight is illustrated in this free body diagram of the pulley, where the weight of the object W acts downward, while the tension in each rope segment T acts upward. In equilibrium, the upward tensions in the two rope segments together balance the downward weight of the load, giving the equation 2T equals W. Consequently, the tension in each segment is half the weight of the load, meaning the effort required to lift the load is also halved in an ideal system. The key takeaway here is that in a system with movable pulleys, the effort required to lift a load is greatly reduced. The effort force can be calculated as the load divided by the number of rope segments supporting the load. This principle highlights the mechanical advantage of such systems, enabling the lifting of heavy objects with less effort by effectively distributing the load across multiple rope segments. Now, what is mechanical advantage? It's a measure of how much a machine amplifies the input force, in this case F, to perform work. It is defined as the ratio of the output force, load, to the input force, effort. In this example, the load, output force, is W, and the input force, effort, is F. Since we found that the effort is half the load, the mechanical advantage of this pulley system is 2, which is the same as the number of supporting ropes attached to the movable pulley. While the mechanical advantage of a pulley system significantly reduces the effort required to lift a load, it does come with a trade-off. In an ideal system, where energy losses due to friction or other factors are ignored, the principle of conservation of energy ensures that the energy input equals the energy output. This means that the work done by the effort force is equal to the work done on the load. As a result, although the required force is reduced, the distance over which this force must be applied increases proportionally. This trade-off between force and distance maintains the energy balance inherent in such systems. If we denote the distance traveled by the load as L and the distance traveled by the effort as X, we can express the energy balance of the system mathematically as follows. Earlier, we determined that the effort is half the load. By substituting this value for the effort into the energy balance equation, we derive an expression for the distance traveled by the effort as 2L. This implies that while the effort required to lift the load in the pulley system is significantly reduced, the trade-off is that the distance the effort must travel is doubled. This outcome perfectly illustrates the conservation of energy, where a decrease in force is compensated by an increase in the distance over which the force is applied. I hope what we've covered so far is clear. If you've been following along, you should now have a solid understanding of how pulley systems reduce effort while maintaining energy balance. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. Let's take a look at this example to better understand the concepts we've been discussing so far. Here, we have a system of 3 pulleys, one of which is a movable pulley. As you may recall, to achieve a mechanical advantage, there must be at least one movable pulley. A weight of 90 Newton is attached to the movable pulley, supported by 3 segments of rope. We need to calculate the effort required to lift the load, determine the mechanical advantage of the system, and find out the distance the effort will travel if the load moves 1 meter. Under ideal conditions, the tension along the length of the rope is uniform and equal to the applied effort F. This uniformity stems from our earlier assumptions. The rope is weightless and inextensible, and there is no friction in the pulleys. Finding the effort required to pull the load is straightforward. In this system, the load is supported by 3 segments of rope, with each segment equally sharing the task of lifting the weight. This is evident in the free body diagram of the movable pulley. Since the total upward force needed to balance the weight is evenly distributed across the 3 segments, each rope segment supports 1/3 of the load. In other words, the effort, which equals the tension in the rope, is 1/3 of the load. This means that the force required to lift the load is significantly reduced thanks to the distribution of the load across the 3 supporting rope segments. Mechanical advantage is defined as the ratio of the load to the effort, and therefore we can easily determine the mechanical advantage as 3. This value also corresponds to the number of rope segments supporting the load-carrying pulley, highlighting a simple rule for calculating the mechanical advantage in such systems. The distance traveled by the effort, corresponding to the 1 meter traveled by the load, can be calculated using the energy balance equation. In an ideal pulley system, the principle of conservation of energy applies, meaning the work done by the effort equals the work done by the load. This relationship can be expressed as follows. Here, F represents the effort force, D sub effort is the distance traveled by the effort, W is the weight of the load, and D sub load is the distance traveled by the load. This relationship ensures that the work done on the load equals the work done by the effort in an ideal system, adhering to the principle of conservation of energy. By substituting the appropriate values into the equation, we can calculate D sub effort, which represents the distance traveled by the effort. This calculation highlights the trade-off between force and distance in pulley systems, showing how a reduction in required effort comes at the cost of increased distance. I followed these steps to show, step by step, how to calculate the effort required to lift a 90 Newton weight and the distance the effort will travel when the load moves a distance of 1 meter. However, you don't necessarily have to follow these steps in detail. You can simplify the process by first determining the mechanical advantage. Just count the number of rope segments supporting the pulley connected to the load. Then, use this value to directly calculate the effort required to lift the load and the distance the effort needs to travel to lift the load by the desired amount. It's worth noting that in more complex pulley systems, identifying the number of rope segments supporting the load may not be straightforward. Don't worry though, in the next video, we'll explore such challenging examples to deepen our understanding. Thank you for watching this video all the way through. I hope it gave you a solid grasp of the mechanics behind pulley systems, how to determine mechanical advantage, and the relationship between load, effort, and the distances they travel. We also touched on how the principle of conservation of energy plays a role in these systems. If you found this video helpful, please give it a thumbs up, share it with your friends, and subscribe to the channel if you haven't already. Your comments mean so much. They encourage me to create more content and help me improve for the future. Until we meet again in another video, take care and goodbye.